Alright, how does equilibrium play a role in solubility? Here I'm giving that calcium phosphate has a certain equilibrium constant when it's dissolving in water, but what does that mean? And how do you use an ice table to solve it? Well, when a solid dissolves in water, we write it like this in terms of chemistry or chemical reactions. The solid is in equilibrium with its aqueous ions. What ions did this originate from? Well, if you remember the crisscross rule of where these subscripts came from, or if you just look at a periodic table and notice that calcium is in the second column, you'll know that it breaks up into a calcium 2+ ion. That's really the only charge I've ever seen calcium have, and it's aqueous because it's now dissolved in water. Phosphate ions, PO4s, have a charge of -3. They're also aqueous. But the deal is that we have 3 calciums and 2 phosphates. So this is my balanced chemical equation for the dissolving of calcium phosphate. To figure out the solubility at equilibrium, we're going to need to do an ice table. As soon as well, this is an equilibrium arrow that I've drawn here. As soon as you know that it's an equilibrium, you should probably do an ice table. Well, we're going to start here with my initial concentrations. The initial concentration of this doesn't even really matter because it's a solid, and solids don't really play a role in equilibrium. The initial concentration of each of these ions is clearly 0 because we're starting only with solid, and how much of, we start with none of these in solution. The change, well, we lose some of this solid, but again, it doesn't matter. We end up gaining some calcium. I'm going to say that the number of moles per liter of this that dissolved is X, and I get 3 times as many calciums as I lost of this. So I'm going to say that this is plus 3x. The 3 comes from the coefficient here, and I gain 2 phosphates for each of those steps. So my equilibrium concentrations of calcium is 3x moles per liter, and my equilibrium concentration of phosphate is 2x. Why does this matter? Well, because we were given K, the equilibrium constant of 2 times 10 to the minus 29, we can use these concentrations in a KSP expression and solve for X. KSP, as you create an equilibrium expression, is products over reactants. Calcium to the power of its coefficient, phosphate to the power of its coefficient, and we don't include the solid in the denominator because it's a solid, and we don't include solids in the equilibrium expression. Now we fill in what we know from the final row of our ice table. The KSP was given in the question, 2 times 10 to the minus 29. Our calcium concentration is 3x, that's cubed, and our phosphate concentration is 2x, that's squared. Let me just take a moment to simplify that for you. 3 cubed times 2 squared is 27 times 4, which is 108. X cubed times x squared is x to the 5. Ooh, look at this. Algebra is useful. How do we solve for x? Well, basic math says we divide both sides by 108. That causes it to get canceled out here. That gives me 2 times 10 to the minus 29. Divided by 108 gives me 1.85 times 10 to the minus 31. And how do I undo it to the power of 5? It's called the 5th root. That 5th root cancels out to the power of 5. On your calculator, you may prefer to just use your to the power of button. It's to the power of 1/5, or again, if you don't like fractions, it's 1.85 times 10 to the minus 31 to the power of 0.2. Let's just do that on my calculator here. to the power of 0.2 or 1/5 or fifth root. And what I end up with is 7.13 times 10 to the power of 367. Cool. I've solved for my x, and it's 7.13 times 10 to the minus 7. That is the solubility in moles per liter of calcium phosphate. If they asked you for the equilibrium concentrations of calcium, it's 3 times that number. If they asked you for the equilibrium concentration of phosphate, it's 2 times that number. But the point I'm trying to get across to you is a solubility question, if you're given KSP, is the same as all other equilibrium problems. Use an ICE table, use your expression for K, plug in your values, and solve for X. It's a beautiful thing, just like you are, my friend. Take care, and best of luck.